Sorry, that just got out of focus immediately there. All right, so I'm working at 2.53 times 10 to the 10 divided by 180. All right, so the frequency is 1.405 repeat times 10 to the 368. Okay, and the unit would be the hertz. Now we can go ahead and put that into our equation here. 3E8 divided by 1.405, repeat, E8. I got 2.13 meters. Okay, question number 3. For the EMR wave shown, determine the frequency of its source electrical vibration. All right, so when we look at this graph, you can see that how many full wavelengths do we have can be determined from this, right? This would be one full wavelength from here to here, and then this would be two full wavelengths. So one wavelength here, and then one more wavelength for the second part, making it two full wavelengths. So 2 lambda is going to be 9.0 kilometers. That means the wavelength must be 4.5 kilometers. Now the frequency is going to be the speed over the wavelength. So 3 times 10 to the 8 divided by 4.5 E3. Convert that to meters, please. All right, I'm looking at 6.7 E4. Okay, and of course you can check your work down here if you need to. It's a good idea. Question number 4. A DC transformer is set up to create radio waves. Describe the nature of the EMR when the switch is closed just once. Why? All right, well, once the switch is closed, then the current starts to increase, which does generate a changing current or increasing current in the secondary coil. So when the switch is closed, the current increases. In the primary coil. Sorry. Okay. Which creates or causes a current to flow in the secondary coil. Creating sparks or a spark across the gap. But once the coil, once the current stabilizes, so once stabilizes or is constant, then of course no current will be induced. In the secondary coil. Because what you need to have is, of course, a changing magnetic field. Okay? To induce current. All right, looking at question number 5. Question number 5 says, consider the carrier waves of 2 radio stations. Compare these waves in terms of wavelength, speed, and time to travel 45 kilometers in microseconds. So we'll just start with the AM waves. So we're going to turn them in terms of wavelength, speed, and time. So for what we have first, which is AM and FM, so the waves, wave, and then we want the following characteristics. We want to have wavelength, speed, time to travel. So wavelength, speed, time to travel. We want it to travel a total of 45 kilometers. Okay. All right, so we're going to start with the AM wave. What's the wavelength here? Well, let's do the calculation. We have 820 kilohertz, and so we have 3 exponent 8 divided by the 820 exponent 3. Okay, so the wavelength is 366 meters. The speed should be c, and the time to travel 45 kilometers, think about your time is distance over speed. So the distance is 45 kilometers, and the speed, of course, is 3 exponent 8. 1.5 e negative 4. And for FM. So now we can go ahead. I just want to grab the number there, 963 megahertz. 96.3 megahertz. Okay, so I've got that. Now let's do the wavelength. 3 exponent 8 divided by that number. We've got 3.12 meters. The speed should still be c, and the time to travel 45.0 kilometers, well, same thing, 1.50 e negative 4 seconds. Okay. All right, I'll finish up the last couple in just a moment. Okay.